Let's dive right into this explainer on direct-to-film, or DTF print production. Today, we're focusing entirely on a phase that literally makes or breaks your entire operation, the artwork pre-flight stage. Think of this process not just as some quick file check, but as your shop's economic firewall. You know, a lot of production pros focus heavily on their press, the powder shaker, all those environmental controls. And hey, those are absolutely vital. But as we're going to see today, absolutely none of that expensive hardware can compensate for what happens before the file ever even hits the RIP software.
Just think about the stark contrast in operational cost here. When you catch an error at the pre-flight stage, say a weird sizing issue or a bad transparency fade, fixing it costs you pennies. Literally just a few seconds of a designer's time. But if you let that flawed file pass all the way through to the heat press, you're not just losing seconds anymore. You are losing the physical garment, the printed transfer, and the heavy labor required to actually press it. Your margins are just instantly destroyed. Pre-flight is where you actually protect your profit.
So, the whole premise really boils down to the quote you see right here. A flawless DTF setup cannot save a fundamentally flawed art file. This is just an undeniable fact to the print industry. We really need to shatter this common misconception that buying the absolute best, highly calibrated hardware will somehow magically make up for bad files. It won't. Predictability on the press demands absolute perfection in the file prep. So here is our agenda to achieve that perfection. First, locking resolution. Second, eliminating halos. Third, handling transparencies. And finally, the operational impact. All right, let's jump right into Directive 1, locking resolution and physical size.
And that brings us directly to the magic number 300, true 300 dpi. We are not talking about a 72 dpi image that you just upscaled in Photoshop, and definitely not some low-res web JPEG where you're just crossing your fingers and hoping for the best. Every single piece of artwork must be standardized to a true 300 dots per inch. If you don't start with this exact data density, you are quite literally setting your RIP software up for failure from minute one.
But it's not just about hitting that true 300 dpi, right? You absolutely have to lock in the physical artboard size before it ever hits the production floor. So as an example, if you're printing a standard adult chess graphic, you need to set that artboard to exactly 28 centimeters, or about 11 inches wide. Why does this matter so much? Because if you feed a tiny file into your RIP software and just rely on the machine to stretch and upscale that image to fit the shirt, you're introducing this massive, dangerous variable. The RIP is often going to generate these unpredictable upscaling artifacts, jagged edges, weird color shifts, you name it. By locking the resolution and the physical size during pre-flight, you remove that guesswork entirely.
Moving right along to Directive 2, eliminating the white halo. If you've been in DTF for a while, you know the halo. To eliminate it, we use a technical protocol called choking. Choking the underbase means you intentionally shrink that white ink foundation layer by exactly 1 to 2 pixels. Now, the white ink underbase is absolutely essential. It's what gives your DTF transfers that bright, popping opacity on dark garments. But we have to make perfectly sure that the colored CMYK layer sitting directly on top of it completely covers that white edge.
Let's look at the mechanics of this. On the left, we see a fatal flaw, a 1-to-1 edge match. If your white ink prints at the exact same edge boundary as your CMYK ink, any microscopic registration shift on the physical press, and they will happen, causes that white ink to just peek out, giving you this highly visible, ugly white halo around the entire design. On the right, though, is the bulletproof solution, applying a 1 to 2 pixel choke at pre-flight. This just pulls the white ink back just enough so that the CMYK ink overlaps the edge, completely hiding the foundation layer and giving you a flawless, crisp graphic every single time.
Now, that brings us to Directive 3, transparencies and edge feathers.
Okay, so we've all been here. Have you ever wondered why these beautiful, complex designs with drop shadows, smoke effects, or soft glowing edges look totally amazing on your monitor, but then turn into an absolute disaster on a DTF transfer? It's a really crucial question for anyone on the production side because semi-transparent pixels are exactly where our digital ideal violently clashes with physical reality.
Let's break down exactly how this failure happens, step by step. First, those raw semi-transparent pixels hit your RIP software. Second, the RIP software just gets incredibly confused. See, it relies on solid data to know exactly where to lay down that white ink underbase. So when an edge slowly fades out to 0% opacity, the RIP really struggles to assign the proper white ink density. And third, because of that confusion, it ends up laying down unpredictable amounts of white ink, which then causes your hot melt adhesive powder to stick exactly where it shouldn't. The end result? These harsh, chunky, completely unprintable borders where there was supposed to be a smooth, beautiful fade.
So the protocol to fix this is strictly mandatory. You must apply an edge feather. You literally cannot rely on a raw transparency fade in DTF. By processing the artwork to include an edge feather, you're proactively creating a clean, defined, printable boundary. You're essentially doing the math for the RIP software ahead of time, telling it exactly how to transition the ink. This simple step ensures the powder only bonds exactly where it's intended to, which gives you that incredibly soft look without any of the harsh, messy borders.
And finally, let's look at the resolution, scaling through strict consistency.
Mastering these 3 directives, locking your resolution, choking that underbase, and applying those edge feathers? Listen, this is absolutely not just about on-screen aesthetics. It's about directly driving your operational profitability. When you actually implement these strict pre-flight rules, you immediately experience significantly reduced variability at the press itself. You practically eliminate file-related reprints, and this leads to drastically reduced touchpoints. Your operators aren't stopping production to troubleshoot bad art, they're just hitting print. Ultimately, your entire schedule benefits from this improved consistency, because remember, high-volume production only scales when it becomes entirely predictable.
I want to leave you with a thought, maybe a bit of a challenge. Look at your shop floor right now. If your printers, your shakers, and your heat presses are highly calibrated and predictable, why are you still accepting unpredictable files? It's time to stop fixing errors at the press, build your pre-flight firewall today, save those pennies, and aggressively protect your margins. Keep learning, keep standardizing, and I'll catch you in the next explainer.